there needs to be desired relative motion. So if this table right here is perfectly flat, perfectly level, and this is sitting on top of it, there's no friction there. If the table became frictionless, if in an ideal situation, this is not going to slide one way or the other. However, I have these right here, and there's a slight slope onto it. I put a marker there. If it were frictionless, that marker would slowly be sliding down the ramp. So friction does act there. There's desired motion, even though there's enough friction to keep it from moving. So it doesn't have to move for there to be friction, but it has to want to move. Direction of the forces in the pair. They are anti-parallel. Well, all of them are anti-parallel, but these sort of overlap. And again, we will go into more detail on those. And with respect to the object, it is parallel to surfaces of contact. So friction and normal force are perpendicular to each other. And these forces will cover us for a good chunk of the course. Depends on how far we get. There's a buoyant force, which would be thrown in there, and electric force, magnetic force if we get far enough. Oh, other. I didn't explain other. Questions before I talk about the nebulous other? All right. Other has two purposes. One, there is actually a reason to have other, but also I needed a valve, or F-town. Oh, yes, Sasha.
Are there symbols for tension and friction?
Oh, yes, there are. Thank you very much. Tension, the symbol, F with the lowercase t. I used to use capital T, but at some point later on in the course, there is a formula which will involve tension and period we use capital T for that. And so instead of using capital T for tension at this point, and then later on going, all right, forget using T for tension, we're now using T for something else. We just start with FT. And for friction, I use what I call my Baroque F, sort of a fancy lowercase f, a little bit of flair. For those bad calculus, almost like an integral sign across through it. Other questions before we talk about other? Let's get to it. All right, so the requirement is I need a force for which I don't know what's causing it, or I don't care what's causing it. And when I say I don't care, this is not your own personal philosophy about the course. It is within the context of physics. Assuming that you love physics, it really does not matter what's causing the force. So the requirement, first off, it's problem specific. And that's a Harvard marker. It is problem specific. And sort of don't know or don't care source of force. I push in on a box with 5 newtons of force. The fact that I'm pushing on the box with 5 newtons of force probably is irrelevant. That would be an example of other. Other shows up typically in textbook problems. The direction of the pair, when you're dealing with others, since you don't really care about half of the pair, this really direction of forces in pair with respect to each other does not matter. And the direction of the force with respect to the object, this is problem specific. use some of this stuff. Well, at least use the idea of forces. A box has a 5 Newton force acting on it. Whenever you're given a problem, I strongly suggest you actually draw a picture of it. So we have a box, or let's just say a 5 Newton force. Pushes on a box to the right. So first off, we're just going to draw it. So I draw my box to the right, that way, so I'm going to draw the force going that way. This is an example of other, because I don't know what's causing that push, it's just, there's something there. Somewhere there's this nebulous object over here with a 5 Newton force pushing back. So they come in pairs, and each force in that pair will always point in an opposite direction as indicated there. But this is something that is built here. One of the things I've just drawn here, this is known as a force diagram. Force diagrams is something that we will do throughout the course. It's how you take a complex, potentially complex problem and break it down into something manageable. All right, so let's just start with a simple question of what is the total force acting on the box? Don't make it more complicated than it is. What is the total force acting on the box? Nay?
Is it 5? 5? Is it 5?
All right, you got partway there.
5 Newton.
All right, we're far closer there. I'll apply 5 Newtons. Sorry? Oh, sort of, I would say implied, but missing another important piece.
To the right?
There we go. Force is a vector, which means there's a size, the 5 Newtons, and a direction. Direction matters. So the total force is 5 Newtons to the right. Now, as a physicist, I don't feel like writing to the right. It's a lot of words. So I want to come up with something shorter, an abbreviation. So there are some accepted ones. One of the ones, instead of to the right, I could just come up with a symbol to represent to the right. So I'm going to draw an arrow to the right so that because I'm defining it, and I'm drawing just taking the letter I and putting a roof over it. The typically spoken of as, this is I hat. If you ever see the hat on top of it in physics, this tells me that we are dealing with a unit vector. It's a vector, so it has to have a magnitude and direction. The direction is to the right, but what is the magnitude of a unit vector? Someone take a shot at it. Magnitude of a unit vector. I'll give you a hint. It's called a unit vector. Pardon?
5 units.
No, that would bring in, that brings the specific problem to it. Although that would be another hint, that in this problem, it's 5 units. It's meant by unit.
It's a number, right?
Yep, what number?
1?
Yes. The magnitude of a unit vector is 1. There are no units attached to it, it's just the magnitude is 1. The whole purpose of the unit vector is to give a direction. So I don't have to write out all these words, I can just simplify it into just I hat. So my total force, 5 newtons I hat. And because I've defined I hat as to the right, I don't have to write out to the right. What's the total force acting on this box?
3.
There we go. Questions about how we got 3 newtons I hat, or what this means? Because I'm about to make it look more complicated.
I have a question.
Yes?
So why don't you have to put the arrow anymore? The arrow to the right, why don't you have to put that anymore?
Well, I don't have to put this anymore?
Yeah.
Because right here, this is defining, this says wherever you see an I hat, that means that way.
Oh, okay.
That just means only right.
Yeah, because I said so.
Okay.
Yep. If I said I hat was up, then this would not work anymore.
Okay.
I'd have something leading to that, going that way. All right, here we go. Let's make it look more complicated. Still sticking with I hat to the right. What is the total force now?
It's going left now.
It is indeed going left.
Yeah.
Therefore, what do I need to do?
Put an arrow?
Square, no.
All right, I heard 2 different things and both of it too quiet. Tinnitus. So, Logan or Nay, I heard your 2 voices.
Oh, yeah, I mean, I had no clue.
Need a
Okay.
different symbol to represent going to the left, not the right.
Have to write even more? There's a simpler way.
If this was the arrow left.
I could I could erase the arrow on one side and go to the other side, but I don't wanna do that,
Do you take
because I don't
the-
wanna. Pardon?
Do you take the little hat out?
No.
No.
Yeah.
Do you put it in front of the 3?
Oh, no. No, if you put the I hat in front, that means the same thing as at the back, just traditionally it's put in the back.
Put a negative on
There we go. Think about a number line. If I got a number line here, positive and negative, positive 5 goes from here to there, negative 5 goes from here to there. Negative means the other way. So it's negative 3 newtons I hat. That's supposed to be an I. Now, if instead we had flipped the I hat and go in the other direction, then yes, that is also legitimate. But oftentimes in problems, you'll have forces going in, say, 2 directions like that, and you just need to decide which way you're gonna make positive, which way you're gonna make negative. Let's do one more of these, and then I'll show you a shortcut that works sometimes. Please don't apply it in every case, as some students like doing. I'm gonna say to the right is positive, or is I hat. All right, what is the total force acting now? Not looking for a name, looking for a value.
Minus
Minus
5 newtons I had.
minus 5 newtons I hat?
Yeah. Maybe, I don't know.
What about the 3?
That's what I said, 3 newtons I hat minus 5 newtons I hat.
Ah,
Sort of maybe.
so 3 newtons I hat minus 5 newtons I hat,
Yeah.
which equals?
Negative.
Minus 2.
Newtons I hat.
Negative 2 newtons I hat.
Yeah.
Ultimately, I should be able to write down a force. I don't have to, I shouldn't write down the math equation that I can still simplify. And what this tells me is that the total force acting on this box is 2 newtons of the magnitude and in the negative I hat direction. So 2 newtons to the left, or in shorthand notation, negative 2 newtons I hat. The negative sign is associated with the direction, but traditionally you write it up front. Please be careful if you want to put it in a different place. I have seen students do 2 newtons in the negative I hat direction. This means something different. Written like this is 2 newtons minus I hat, which actually can't simplify anymore. If you want to put the minus there, then put parentheses around it or something to indicate that it's not a subtraction problem. Questions before I make it a little more difficult?
And we kept the negative in front of the 2 because the 5 is pointing to the left?
Yes.
Okay, that's what we're doing.
Yeah, I mean,
Because I was gonna keep it as a positive.
from just a straight up elementary math point of view, 3 minus 5 is negative 2. But from a physics point of view, I got more pushing to the left than I have to the right. Other questions? All right, let's make it a little more difficult. Oh, the shortcut. Sorry, let's do the shortcut first, and then we'll make it a little more difficult. If it is a one-dimensional problem, and so it has to be a one-dimensional problem, as in the forces are along a line. So this would be a one-dimensional problem. You can use plus instead of I hat. So for this problem right here, I could have just done, because it's a one-dimensional problem, I could have just done a plus sign right there, and then done 3 minus 5, which is negative 2, and then make sure the units are there. If it's not a one-dimensional problem, don't do this. If you going with I hat every time, that's fine, that works. But there are times it's convenient, I don't feel like writing the I hat down. I don't have to in special case. All right, let's make it look more difficult. Take a shot at it? Everyone in here is going to make mistakes, so you know, you just.
Is it multiplication?
It is not. It would still be an addition problem.
Would be 8. Would be 8.
No. It would be 8 if they, well, the 8 would be magnitude, throw in some units, if they were in the same direction, but they're not in the same direction. It's a two-dimensional problem.
You need 2 symbols?
What would you suggest?
One symbol representing up and the other one representing right.
Okay, so I'm gonna pick I hat to the right. and up j hat.
So then your equation would be 5 in I hat and plus 3 in j hat.
Exactly. And done. Where I've got the I hat and j hat, I haven't combined it, I can't simplify it anymore as is. This is known as rectangular form. But when you get to 2 dimensions, this is why you can't get away with just using a plus sign, because I have 2 different positive directions, and if I just made them both positive, it would look like the answer is 8 newtons, and it's not. Let's extend this a little bit further. I want to know what is the magnitude of the force. So I got my force here. I want to find the magnitude, so I can use absolute value signs that says I want just the magnitude. I could also write that as F without the vector symbol over it, indicating I want the magnitude of the force. And the answer is not 8 newtons. I need to somehow add these and come up with a single number. So let's do it. When I have something like this, I'm going to add in what's known as the head-to-tail method. Hewitt refers to something known as the parallelogram method. It works the same as what I'm doing if you're dealing with just 2 vectors. If you have more than 2 vectors, then parallelogram method is a nuisance. There are lines drawn all over the place. I would not recommend it. Head-to-tail method will work no matter how many vectors that you have. And erasers over here. So we're going to do some vector math. Does direction matter? So it was 5 newtons to the right. So I'm just going to draw a 5 newton vector to the right. I don't have to write I hat because I'm indicating the direction of the vector right there. And then 3 newtons up. This is known head to tail. This is the head of the vector right here, the arrow head. The tail is the one that doesn't have the head there. And then I draw